Hello and welcome. We'll be solving another interesting question under bending stresses in a beam. Alright, the question says a square beam 20 mm by 20 mm in section and 2 meter long is simply supported at the ends. Alright, so the beam fails when a point load of 400 Newton is applied. Alright, so first statement there, that is everything that I read this place. This is the diagram of the simple supported beam, which is 2 meter and loaded at the center with 400 Newton, and this is the square section. This 20 meter by 20 mm by 20 mm. All right. So, and the question now says, what uniform distributed load per meter length will break a cantilever of the same material 40 mm wide and 60 mm deep and 3 meter. All right. So the given data here is the given data for a simple supported beam. So I'm still going to be drawing a cantilever beam, and with the section too, I'm going to draw it. All right, but before we go into that, we need to calculate the maximum bending moment for this simple supported beam. That is, sorry, we need to use this information given to us to calculate the maximum stress, because the maximum stress for this simple supported beam will be the same with the cantilever beam. Why? Because they said they are made of the same material. So we need to find the maximum stress with this information. And for us to do that, we'll be starting with the what? Section modulus. All right. So we know that the section modulus Z is equals to what? BD square divided by what? BD square divided by 6. All right. So we are going to substitute there. It's going to be 20 multiplied by 20 squared divided by 6. All right. So if you punch this in your calculator, you are going to have this to be equals to that is 4,000 divided by 3. Then your unit is going to be mm to the power of 3. All right. So that is what we are going to have. I did not simplify it, just leave it like this at the moment, and you can decide to write your answer that your calculator gives to you. All right. So now that we know the section modulus, so we can therefore calculate the maximum bending moment of this simple supported beam that carries a point load. If you watch our video on the practical application of flexural equation, I have explained the maximum bending moment for a simple supported beam that carried a point load, and the formula for that is nothing but maximum bending moment will be equals to what? Will be equals to WL divided by what? By 4. All right, so this will be equals to the load there is 400 multiplied by the length. The length is 2, then divided by 4. So here we are going to have 200 as our answer. All right, but it's going to be 200 Newton meter. 200 Newton meter. All right. So the next thing you are going to recall here is from the modification of our flexural equation. We've already told us that our maximum bending moment is equals to maximum stress multiplied by what? Multiplied by Z. That is the sectional modulus. All right. So if we make our maximum stress the subject here, so our maximum stress will be equals to maximum bending moment divided by Z. So if you substitute now, we are going to have our maximum bending moment multiplied by, so don't forget that this one is in meter, right? and this one is in millimeter. So for us to convert this to millimeter, we are going to multiply by what? 1000. So this is going to be 200,000. 200,000 divided by what? Z. Our Z is 4,000 divided by 3. So if you to arrange this, is going to be 200,000 multiplied by 3. So it's going to be multiplied by 3, then divided by 4,000. So we can clean this now. All right, so that is what we are going to have. So our final answer here is going to be 150 Newton per what? Per millimeter square. So this will be the maximum stress, maximum bending stress for this information provided for us. So we are going to be drawing a cantilever beam, and then we are also going to be drawing the we are going to be using this information provided for us to draw the cantilever beam. All right, so let's draw the cantilever beam now. All right. All right. I just love my work to be very, very neat. All right, so this is a cantilever beam. And then, so we are told that the length is 3 meters. So it's 3 meters. All right. So this is 3 meters, and it's carrying a uniform distributed load. All right. So now the section is 40 millimeter wide and 60 millimeter deep. All right. So yeah. All right. So here is going to be 40 millimeter wide. All right. So the depth is 60. So please ensure your work is very, very neat when you are solving engineering questions, and you have to be very, very fast. Right? You have to be very, very fast. Then the depth is 60. All right. So this is the information. So let's bring out the given data here now for this cantilever. Given data now. All right, so the base is 40 mm and the depth is 60 mm and the length is 3 meter. All right, so and do we have the weight of the cantilever for the UDLA? So what uniform distributed? Okay, so we want to look for the weight, that is load on this cantilever of this UDLA on the cantilever. So per meter length, it's going to be per meter length. All right, so this is what we want to look for. All right, sorry please. All right, so now we can proceed. So again, we are going to be looking for the what? The sectional modulus of this section. So we are going to start with z, so which is bd square divided by 6. So if we substitute here, we have a b to be what? 40 multiplied by d is 60 divided by 6. So if you punch your calculator correctly, you are going to have this to be 24,000. 24,000. Then your answer is going to be mm to the power of 3. All right, so that is it. Now the next thing is we are going to go for our maximum bending moment for this cantilever beam. All right, we have also talked about the maximum bending moment for this case of cantilever. So if we have a cantilever with a uniform distributed load, the maximum bending moment, the formula for that is going to be equals to WL square divided by what? By 2. So this will be equals to, we don't know what our W is, but we know what our L is. So it's going to be W multiplied by 3 square divided by what? By 2. All right, so if we do this, we are going to have what? We are going to have this to be equals to 4.5. 4.5 W. Then the unit is going to be what? The unit is going to be what? Newton meter, because our length here is in meter. So it's going to be what? Newton meter. So Newton meter. So, but if you want to take it to Newton millimeter, we are just going to multiply by what? By 1000. So we can say this is going to be equals to 4.5 times 1000, then W, then Newton millimeter. All right, so that is what we are going to have. So again, we are going to be applying this formula here again. So we note that from here we've already established that our maximum stress is equals to this multiplied by this. So if we make the if we write this and then we make substitution, okay, so maximum bending moment will be equals to maximum stress multiplied by what? By z. All right, we've already established that because they are of same material, they will have the same maximum stress. So our maximum bend moment for this cantilever is 4.5 multiplied by what? 1000, which is equals to the maximum stress here is 150. So it's going to be 150 multiplied by z. Z is 24,000. All right, so I think it's supposed to be W, it's supposed to have W attached. All right, so for us to calculate this W now, we divide both sides by this. So it means that W will be equals to 150 times 24,000 divided by 4.5 times 1000. All right, so if you punch this in your calculator, you are going to have this to be equals to 800 Newton per meter. So that is going to be our answer for this question. So stay tuned for more interesting content, and I hope this question is well simplified and well understood. You can let us know that in the comment section. And don't forget, if today is your first time coming across our content, don't forget to give this video a thumbs up, and don't forget to subscribe, and don't forget to hit the notification bell so that anytime we upload a question like this, you'll be the first person to receive it. And please don't forget to share our content with your friends who might be in need of it. Thanks. We got you covered.